for section 8.1, we are going to take a look at another type of function, which we call a rational function. And we have a little bit of experience dealing with types of rational functions because a rational function is going to be defined as p of x over q of x, where p and q are both polynomials. And we just got done spending a fair amount of time on working with polynomial functions, quadratics specifically, but some others, cubics and so on. And so what it boils down to is we're going to see what happens if we have a division of 2. We spent a lot of time in the last chapter or so on adding, subtracting, multiplying different polynomials. And so we're going to see what develops when we have a division of 2 polynomials, such as p of x over q of x, for instance. So ultimately, one of our skills here, if we look at on page 430, if you look at number 1, we have one of the rational functions that we're given first is this one, x plus 1 over x squared minus 9. And ultimately, a couple things that we need to be able to do here with this type of function is, number 1, just evaluate it at a particular point. So if we were to put a 1 in there, and we put our 1 in for x in the x positions, we'd wind up with 2 on top. We'd wind up with 1 minus 9, negative 8, and we get negative 1/4. And just like any other function, we could check that with calculator, because we can use our table function. And if we put our y equals, one thing that we need to be careful with here is that when we do have a rational function, that the whole top and the whole bottom be put into parentheses. If you do not do that, you're going to have some trouble in terms of getting the correct values. So x plus 1 and x squared minus 9, and if we put that in there as such, and we go to our table, we can see that at 1 we get negative 0.25, which is exactly what we got by hand, and therefore we know we're correct. And we could do that with any number of x values that we so choose. We could find them with calculator, or we could find them by hand. So in terms of evaluating a rational function, we're just doing the same thing. We're going to follow the order of operations. And one thing important with a rational function, though, is that when we do the evaluation, that this division, the division bar, is essentially a grouping symbol. So we need to figure out what's on top, what's on the bottom, and then the very last thing, we do the division. Now, we don't actually necessarily have to do a division if it's not divisible, but ultimately we need to keep the answer as a reduced fraction. Okay. So the next item is we need to figure out is what is the domain of a rational function. And what it boils down to is to find the domain, we are going to set the bottom of the equation, the q of x part, equal to 0. So to find the domain, set q of x that is equal to 0. Because what it boils down to is with a rational function, one thing that we can't have in math is we can't have a 0 on the bottom of the fraction. If we do, we have something that's undefined. So we want to find out what is going to make the bottom 0. And those numbers that we find, numbers, if we find any, are going to be the numbers that we can't have be part of this function. So we learned how to solve this type of equation last time when we have just an x squared and a constant. We get the x squared alone and then take the square root, and we know that we get 2 answers here, plus and minus 3. So what it boils down to is that x cannot equal plus and minus 3, or else that would make the bottom of this equation 0, and that's not okay. And we can, this is one way to list the domain, but we learned earlier how to list the domain in what we call interval notation. And so remember, ultimately, if we can't have negative 3 or 3, normally if there's nothing that's bad, we just put our domain as negative infinity to infinity. But in our case, we have to go from negative infinity to negative 3, and then from negative 3 to 3, and 3 to infinity. So that would be our domain listed in interval notation by putting parentheses on the negative 3 and the 3 on either side. That excludes those from the interval. And just so we can see an example, if we draw our graph of this, if we do our zoom standard on that, we can see what happens here is that we have 3 different branches of the curve that we see. And at 3 and negative 3, the curve does not touch 3 and negative 3, and we call those vertical asymptotes. So those create vertical asymptotes. And in the case of rationals, when we have a situation where there are numbers that will make the bottom equal 0, there's really 2 choices. They could create asymptotes on the graph, or they could create holes in the graph. And so For the time being, we can notice that it's pretty evident on this one that they're asymptotes because the curves either go up along the asymptote or down along the asymptote. Okay. So, if you would, with me, take a look at on your practice test, you have number 13. So practice test number 13, you have y equals x plus 4 over x squared plus x minus 56. And ultimately here the issue is, can we find the domain? So with that, if we want to find the domain, our rule that we just wrote is going to be to set the bottom, the q of x part, equal to 0 and solve. And so we know how to solve a quadratic equation. Hopefully this factors. If it factors, then that's great. If not, we'd have to use the quadratic formula. Ultimately, our AC here is 56, and we're looking for a difference. 7 and 8 would make 1, so we'd go x minus 8 and x plus 7 if we use our AC method. And assuming that we can all do that at this point, if this is still an issue for you, I would suggest letting me know that so we can get some extra help. So bottom line here is we go x minus 8 equals 0, or x plus 7 equals 0. And if we add 8 here, and we subtract 7 here, we get our two answers. So positive 8 and negative 7 are the two things that we cannot have into the bottom of the equation, or else we'll have a situation where we have 0 on the bottom. So how do we write this in interval notation? So again, we want to exclude these two numbers. So we start with negative infinity again, go to negative 7, go to negative 7 to 8, and then finally 8 to infinity. And that is the domain of our equation here, number 13. So again, this is practice test number 13. Okay. All right. So with that said, if we take a look next at our next task in terms of dealing with rational functions is can we simplify a rational function? And ultimately, this is going to be related to what we learned a long time ago in terms of simplifying, and that's taking something like 4/8. Okay, we can change 4/8 into 2 times 2 and 2 times 4, and ultimately what that allowed us to do is to take out those common factors and leave us with 2 over 4. Now, we also know that 2 and 2 times 2 are factors of 2 and 4, so 2 times 1 and 2 times 4, if you will, and we could reduce that even further and get finally 1/2. So notice the crossing out of the common fraction or common factors here. That's the theme that we're going to look at here in the next part. So ultimately, on page 430 again, we're going to visit number 27, which says 20x to the 7th is equal to 15x to the 4th. So ultimately, this procedure that we used up here is really going to be very similar to what we did here, and we've actually done some problems like this before where we have a division, and we hopefully know what to do from our rules of exponents to deal with this situation. But ultimately, when we have monomial over monomial, it's just going to be very similar to what we've always done in the past, which is reduce the fraction part, the number part, and ultimately 5 can divide both of those, so we'd have 4 over 3. And then the x part, we know that x on top is bigger, and it's bigger by 3, so we'd ultimately get 4/3 x cubed. All right. Now, the question is, how does that change if we have something like number 33, for instance, where it's not a monomial over monomial, it is a binomial on top, and then at the bottom we have a trinomial. And it's x squared minus 14x plus 49. So ultimately, here's the biggest issue that we got to make sure that we do not do. And I'm going to write it in bold here. You cannot cross out parts of binomials or trinomials, or any polynomial for that matter. Alright, so here's what I mean by that. This is a famous technique that some people try, and it's going to be wrong every time. Okay, I got x squared minus 49, I got this here. Oh, they both have a 49, let's cross them out. So now I have x squared minus 14x on the bottom, and I have x squared on the top. Well, can't I just do the same thing with the x squareds then, and cross that out and just get 1 on top and negative 14x on the bottom? The answer is absolutely not, because you cannot cross out parts of binomials or trinomials, or any polynomial for that matter. So the fact that I took the two 49s and crossed them out, those are both parts of binomials and trinomials. Cannot do that ever. Every time we do that, it's going to be wrong immediately. So do not do this. So So put this in your mind and put a big X through it. We cannot do that process. So what do we do instead? Well, ultimately, if we have x squared minus 49 and we have x squared minus 14x plus 49, we need to essentially follow the procedure as follows. We're going to factor the top and factor the bottom. Top, we notice we have a difference of two perfect squares, so we'd have x plus 7 and x minus 7. On the bottom, if we use our AC method here to factor this, we're going to get x and x, and minus 7 would be our factorization for the bottom. And now that we have it in that form, now it's very much like what we had up here. We have 2 and 2 times 2 and 4, and the key is the times. Okay? These are addition and subtraction, so therefore we can't cross things out of additions and subtractions, but we can cross things out when there's multiplication. So ultimately that x minus 7 and that x minus 7 can go. And so our final answer then is going to be x plus 7 over x minus 7, and our polynomial, or rational function I should say, will now be simplified. So the key issue though is factor the top, factor the bottom. If they have any common factors, once it's in a multiplication form, then we can cross them out and be left with whatever we're left with over. Okay. So with that, let's take a look at one more from your book here and look at number 41. So on 41 we have 6x minus 18. We have 9 minus x squared. And it's going to be an interesting result in this case because we have top. We recognize that it's the only thing we can do is GCF. And if we do that, we get 6 times x minus 3. And then we have 9 minus x squared. Those are both perfect squares, so we'd get 3 minus x and 3 plus x. Now the question is, none of those look exactly the same as one another, so can we cross them out? And the answer is yes, but we got to think a little bit here. If we take x minus 3 and we take 3 minus x, say I put a 5 in here for instance. A 5 here would give me 2 on the top. A 5 here would give me negative 2 on the bottom. Okay, the two parts would cross out, but if I had a positive divided by a negative, the answer would be negative. So hence, if we have two subtractions that are opposite of each other, we can cross them out, but instead of them being 1 and 1 like they were up in this example, they're going to be negative 1 and 1. And so therefore my final answer would be negative 6 on top, 3 plus x on the bottom. So those are okay to cross out if they're opposite subtractions, if you will. But we got to cross them out and make one of them negative 1, one of them positive 1, as opposed to what we did up here, which both were positive 1. Okay. All right. So let's take a look at another example here from our practice test. We have practice test number 6, and we have negative 4x to the 5th, and we have x to the 5th minus 4x to the 6th. So again, someone hasty is going to go, oh, cross out the x to the 5ths. And I'm going to say to that, no, do not cross out the x to the 5ths. Okay, because we're crossing out a part of a binomial by doing that. So on the top, though, there's really nothing to do because it's a monomial. But on the bottom, we have a GCF. So factor out the GCF first. And we'd have 1 minus 4x in the parentheses. And now that this x to the 5th is in a multiplication, now we can cross it out. So we can, in fact, cross it out, but we have to do it at the appropriate time. So on top, we'd be left with negative 4. On the bottom, we'd have 1 minus 4x, and we'd be done. And again, don't fall into the trap of crossing out the 4's, because that 4x is part of a binomial. You can't cross it out with something on top, unless it's in a multiplication, which it's not. So, okay. The final one I want to look at here before we carry on to our next lesson is, again, practice test number 7, so we're still on the practice test, just so we have some good examples to look at for when we do our homework problems. We have two polynomials here that, again, if you cross out the x squared, it's going to be wrong immediately, so do not do that, once again. But we can factor, and if we do the top one, we'd get x and x. 42 would be our AC. We could use 7 and 6, minus 7 and plus 6. And then if we factor the bottom, we got x and x, be minus 7 and minus 3. And so if we factor them appropriately, we notice that we do have an x minus 7 and an x minus 7. So we can cross those two out. And our final answer then will be x plus 6 over x minus 3. And we're done. Okay. That will do it for our lesson 8.1. So again, the gist of it is we have rational function, which is a polynomial divided by another polynomial. And so we need to find the domain of such a function by setting the bottom equal to 0 and finding the numbers that can't go into the bottom because it would make the bottom 0. And then the other part is to take a rational expression like the ones we've studied here and simplify them by using our factoring techniques and then crossing out any common factors.